Good morning, everyone. Am I audible?
Good morning, sir.
Shall we begin? Hello?
Yes, sir.
Okay. There are only four participants so far. There are others.
Wait, 4, 4, 2, 3.
Are they waiting for any link or something else?
Don't.
Okay, let me start now. So far, what we have seen, we are working in a space where space is a non-linear space. Okay, so far we have talked about non-linear spaces. Okay, so here what we have a vector space X, a vector space, and we have a norm on X. Okay, and this norm introduces a metric D. How do we define this? We define metric like this, and you all know that metric gives the notion of uh, length. So far we have the notion of length. We are working in those spaces where there is a length, a concept of length is there. But a geometric concept that was missing in those spaces was the concept of angles. So see, when we are in R2 or when we are in a plane, then there is this notion of angle. Say this is one, okay. So this is one vector, and this is another vector. So then there is a notion of then there is this notion of angle in geometry that was missing in non-linear spaces. So now we are interested in this concept of angles. So what we do, let's recall first. Recall the usual dot product, well-known dot product. You all have seen this dot product or scalar product. We will not say scalar product, we will say dot product. So what you do, we have two vectors, say A1, A2, A3, say in R3, we are in R3, and B is B1, B2, B3, this is again R3. Then if you remember, how do we define A dot B? Can anyone recall this? Hello?
A1 into B1
Okay, very good. A1, B1 plus A2, B2,
plus A2, B2.
A3, B3. If if you are not able to recall this, then think AH, A1I, sorry, A2J, A3K, BH, B1I, B2J, B3K. I think now you remember what A dot B was. Okay? If you remember this, you must have seen there in your 11th, 12th class when you studied this first. So you define A dot B like this, mod A, mod B, cos theta. Do you remember this?
Yes, sir.
Yeah.
Yes, sir.
Where this theta is the angle between the vector A and B.
Yes,
So
sir.
from this, we have A dot B by mod A, mod B. Okay. So we will generalize this notion of dot product in arbitrary vector space, and we will do this by defining inner product on vector spaces. First, you all have learned this concept of inner product in linear algebra. So I will first define it. I mean, you all know, I will not give you too much details. So let me give the definition first. Suppose we have a vector space X vector space over a field K. So an inner product is a function. So an inner product is a function on X cross X2, where
It's
in
to
field.
K.
Okay. So means for each pair in X cross X, each pair of vectors AB in X, this assigns a scalar in K. Okay. So inner product is a function that assigns each a scalar. Okay. And we denote that scalar by A comma B. And this function satisfies some properties, and it satisfies the following conditions. See here, it is linear. Okay, I'm writing AB. So A plus B comma C is A comma C plus B comma C. So this means this is linear in first coordinate, linear in first coordinate. Okay. So you all know the meaning of linearity. Second thing, alpha A comma B is alpha A comma B. Here it's homogeneous in first coordinate. And this is true. The above was true for all A, B, C in X. This is true for all A comma B in X and for all alpha in K, all scalar alpha in K. Then there is this condition A comma B is same as B comma A whole bar. So here bar means this is conjugate. This bar represents conjugate of, so you know A comma B may be a complex number. So if this is a something a complex number Z, then then BA would be Z bar. Okay. So do you all know what is conjugate of a complex number? If Z equal to X plus IY is a complex
Conjugate.
number, then Z bar is X minus IY. Okay. So we will observe something from this third equality, third condition. Then fourth one is positive definiteness. So take A comma A is this is always greater than 0 for all A in X. In fact, what I did here, yeah. In fact, this is 0 if and only if A is 0. Okay. Now observe few things. So from 1 and 3rd, C A comma B plus C is same as B plus C comma A bar. Correct? Okay. So then this is B comma A plus B C comma A bar. Okay. So this is nothing but A comma B plus A comma C. Okay, here this is linear. Now, second thing is A comma alpha B. From third, AB is A bar. Okay. So this is alpha B A bar. Correct? Now, what is alpha A? Alpha AB is alpha A comma B. So this is bar of alpha B comma A, which is equal to alpha bar comma B comma A bar. So which is alpha bar, but BA bar is AB. So this means, so from these two, you see inner product is linear in first coordinate, but it is not linear in second coordinate. So here it was okay. Here it was okay, but in this part, you are getting alpha bar AB. So this means it is not linear, but it is conjugate linear. get linear in second coordinate. Okay, so this is by definition of inner product. Inner product is conjugate in second coordinate. So we call such functions which are, so it is in fact a functional. You see here, not functional, but exactly not functional. Functional on x cross x. Okay, so it's conjugate linear in second coordinate. So such kind of functions are called Cauchy linear functional. Linear functions. So a norm is a Cauchy linear function. Okay. What did I say? A norm. I said a norm, no? Did I say norm?
Cauchy linear function.
और
So it's not norm. Sorry, it's inner product. Inner product is a Cauchy linear function. Okay. So Cauchy linear means it is linear in first coordinate, but it is conjugate linear in second coordinate. So a vector space X, which is equipped with an inner product, it's called an inner product space. Okay, so we will see that these inner product spaces are always normed spaces. We will see this, and you know all normed spaces are metric spaces. Therefore, inner product spaces will be metric spaces. And since you know, in metric spaces we talk about complete metric spaces. So if we complete inner product space has a name, it is called Hilbert space. For normed spaces, if we complete normed space with Banach space, here if we complete inner product space, it's called a Hilbert space. So every Hilbert space is a Banach space, but converse is not true.
तो नॉर्म्ड स्पेस और जो ये भी हम प्रोडक्ट स्पेस है तो इसका कोई एक्सटेंशन देख सकते हैं एज अ एक्सटेंशन देख सकते हैं इन प्रोडक्ट स्पेस को
हाँ, ये मोर जनरल है ना.
ओके
देखो नॉर्म स्पेस में हम लोग बात नहीं कर पा रहे थे एंगल की, वो यहाँ पर बात करेंगे. सो दिस इज मोर जनरल स्पेस. ओके, करेक्ट.
सर
ओके, आपका क्वेश्चन क्या था, एक बार रिपीट करेंगे.
सर नॉर्म्ड स्पेस को एज एन एक्सटेंशन देख सकते हैं हम सॉरी इनर प्रोडक्ट स्पेस को एज एन एक्सटेंशन देख सकते हैं हम स्पेस
किस सेंस में एक्सटेंशन देख रहे हैं आप?
सर प्रॉपर्टी वाइज
आप कह सकते हैं कि ओके, लेट्स सी दिस एज एन
सर व्हाट यू
एक्सटेंशन
वांट
ऑफ.
टू से एग्जैक्टली सर आपने आंसर किसका दिया था तो मतलब इसी का है ना मैं ऐसा
ओके,
कंसीडर
मैंने बोला कि एवरी इनर प्रोडक्ट स्पेस every inner product space, each a normed space. So therefore, every complete inner product space is complete normed space. ओके, सो अभी यहाँ पर देखते हैं. ओके, थोड़ा सा हम पास्ट में चलते हैं जो अभी तक आप पढ़ के आए हैं पीएससी से. एवरी डिफरेंशिएबल फंक्शन इज कंटिन्यूअस. ओके,
सर
सो यहाँ पर अगर हम कोई ओके कोई रिजल्ट हम प्रूव करते हैं इनर प्रोडक्ट स्पेस के लिए, ठीक है, then it will be true for sorry, if we have a result for continuous function, then it will automatically true for differentiable function. Do you see this? So similarly, if we have a result for normed spaces, then
For inner product, sir.
then it will be true for inner product spaces because inner product space is a normed space. Okay,
ओके सर.
बट कन्वर्स हम नहीं कह सकते. कुछ रिजल्ट ऐसे होंगे जो 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 इनर प्रोडक्ट स्पेसेस में हैं वो नॉर्म्ड स्पेसेस में ट्रू नहीं हो सकते, क्योंकि कोई फंक्शन कोई फंक्शन है जो डिफरेंशिएबल है, वो जरूरी नहीं है कि वो कोई फंक्शन कंटिन्यूअस है तो वो जरूरी नहीं है कि डिफरेंशिएबल भी होगा. ओके, सो अगर कोई रिजल्ट में डिफरेंशिएबल फंक्शंस के लिए प्रूफ करता हूं तो it need not be true for continuous function. So same analogy यहाँ पे, ठीक है. ओके,
सर
आप समझे?
यस सर समझ गए.
Oh, so let's see some examples. So the Euclidean space Rn. So let us define a norm in inner product in Rn. So we have seen so far that Rn is a normed linear space. In fact, Rn was complete normed space. So Rn was a Banach space. Okay. Now let us see whether it is inner product space or not. So let us define inner product on Rn. So take x equal to xi1, xi2, xin, and y equal to eta1, eta2, eta n. So these both belongs to Rn. So let us define what is x comma y, inner product xy. So you may guess what it would be from here. How did we define a dot b, which is a1 b1 plus a2 b2 a3 b3, and I said that we are generalizing dot product. So you guess this. You can guess what would be x inner product xy. It would be
Xi1 eta1.
eta. Okay. So it is not only inner product. There may exist other inner products in Rn. So Okay, so it is an exercise for you to show that this is an time writing. Verify that this xy in Rn is an inner product. Okay, so this is not the only one. So you may define, for example, take R2 n equal to 2 and take R2 and then x equal to y1 y2, y equal to eta1 eta2 and define x comma y by eta1 eta1 as eta2 eta1 and as eta1 eta2 plus 3 eta2 eta2. So this is also a real inner product space. So you may verify that this R2 is an inner product space. Okay, so this means we may have many different inner products on a linear space. Okay, so similarly, this was so on another example, say take CN. So in CN also we do the same thing, but let's define a norm, an inner product in CN. So CN means this is nothing but n-fold Cartesian product of C. So elements of CN are of this form. Are this form, zeta 1, zeta 2, zeta n, Cn, where zeta I belongs to C, means zeta I would be something xi plus iyl. X, okay, zeta j would be xj plus iy. Okay, here this I is correct. So we define, take two elements x and y, the two, the n in Cn. Now we define the inner product y. This is given by eta 1 bar, eta 2 bar, n eta n bar. Okay. So verify that this is an inner product. So consider, for simplicity, take n equal to 2. We will be in C2. Take x equal to zeta 1 zeta 2, y equal to eta 1 eta 2. Okay. Then what you have to show that, take one more, z equal to zeta eta, say alpha. Okay. Take x equal to xi1 xi2, y equal to eta 1 eta 2, z equal to zeta 1 zeta 2. Okay. So then you have to show that x plus y z is same as x comma z plus y comma z. So for this, what is x plus y? You know, it is xi1 which is xi1 plus eta 1 bar plus 2 plus eta 2 bar. Okay, so by definition, this is this, and then this is equal to xi 1 zeta 1 bar plus zeta 1 zeta 1 bar plus xi 2 zeta 2 bar zeta 2 zeta 2 bar. So take this and this, and then take this. So what you get is xi 1 zeta 1 bar plus so xi 2 zeta 2 bar zeta 1 zeta 1 bar zeta 2 zeta 2 bar. So this part is x comma z. This part is y comma z. Correct? Is there any doubt? So similarly, you may prove alpha x. Similarly, you may prove alpha x y is alpha x comma y. But let's see the third one. So x comma y is x comma, by definition x comma y is xi 1 eta 1 bar plus xi 2 eta 2 bar. Okay, so this is same as, okay, this is same as eta 1 bar xi 1 plus eta 2 bar 2. But you know z bar is z. So if z is a complex number, z bar is z. So eta 1 bar zeta 1 bar plus zeta 2 bar, sorry, eta 2 bar xi 2 bar. Correct? So this is nothing but whole bar of eta 1 zeta 1 bar plus eta 2 zeta 2 bar. But this is bar of y comma x. So in this way so similarly you may verify others. Okay, now let's give another example then. Take a so CAB, the space of all C-valued continuous functions on AB. Then we may define f comma g, the net product of f comma g. So f and g both are complex valued continuous functions. We define a to b f t dt bar dt. So you may verify this, that if that this is an inner product. So you have to verify all those 4 or 5 conditions of inner product, 4 conditions of inner product. Okay. Next, let's see a very beautiful inequality, very beautiful result called Cauchy-Schwarz inequality or Schwarz inequality. Sometime it is called Cauchy-Schwarz inequality. Okay. So what does it say? It says if we have inner product space, so suppose this is an inner product space, then for any two vectors x comma y we have order of y is less than equal to norm x comma y. And equality holds if x and y are linearly dependent. X is linearly dependent on y, or we can say x equal to alpha y. Okay. Equality holds if x equal to alpha y. And in fact, this is if and only condition. Let's see a proof. I think I know you have already seen a proof of this. You know a proof of this. Somewhere you have seen it. I don't know where. In linear algebra course or in your BSc. So let's recall again. Okay, suppose y equal to 0, then there is nothing to prove because x comma 0, this is 0. So, and when y is 0, norm y is 0, correct? So both right hand and left hand side are 0, which is norm x, norm 0. There is nothing to prove. So let's take y is non-zero. Hello, am I audible to everyone?
Yes, sir.
Okay, okay. Is there any doubt so far?
No, sir.
Okay. Okay. So here is a trick to prove this. So what we do, we consider. Okay. So before proving this, let me give you one. So I orally told you that in a product space gives a norm, but I didn't give you a formula. So let me first give you a formula for 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 a norm induced from a net product space. Okay, so and digression. Here we take a digression. Okay. Okay, so what I told you that in a product gives a norm. So see, a norm is a function from x to r. Okay, in fact, r greater than 0. And an inner product is a function from x cross x to k. But you see, the last property of inner product space is x comma x is greater than equal to 0. So if we take such kind of things, so we are taking vectors from x only, so there is only one vector from x, and it takes values in here are positive non-negative real numbers. Okay, so it is a very ideal candidate to consider this function. So for norm of x, if we define norm of x is this, but see if so let's see whether we can define this or not. So we know in R2, if we have an element R2 A1 comma A2. So say this is A. What is A comma A? So by definition, A comma A is A1 square plus A2 square. Correct? Is it okay? But you know, norm of A is norm of A in R2 is A1 square plus A2 square root of it. Correct? So what you do, you make square root of this inner product. So we define norm x as xx or norm x square equal to inner product xx. Okay. Oh, not yet, not yet. Let me give you one more thing. So you know, every norm induces a metric. So how do you define metric? Means distance between x and y. What you do, this is norm x minus y. So you can write it in terms of inner product as well. So it will be x minus y comma x minus y, but then there is a root. Okay. So in this way you define metric induced from an inner product. So digression end. Okay, let's go to the proof of this. So let's again see the statement. What we want to prove, we want to prove for an inner product space for any two vectors x comma y, this inequality holds. Said that for y equal to 0, there is nothing to prove. For y equal to 0 or for x equal to 0, there is nothing to prove. Okay, now take y non-zero. That y is non-zero. And use this definition. Okay. So if y equal to non-zero, then for any scalar delta we have, so norm x minus lambda y, this is this trick. So see here, you all by definition of norm, this is always greater than equal to 0. Correct? This is 0 when x equal to lambda y. But we know that this is always greater than equal to 0. So by definition, this is, so here mod x square is inner product x comma x. So norm of this vector is inner product this inner product. Correct? Now use the definition of inner product. So let's do this. Okay, so this is linear in first variable. So this is x comma x minus lambda y plus minus lambda y x minus lambda y. Correct? Is it okay?
Yes.
This is
Yes,
first
sir.
condition. Okay, now it is linear in second, means when we talk about this sum, we call it was a comma b plus a comma c. Okay, and we also saw that alpha a b equal to alpha a comma b, and a comma alpha b was alpha bar comma b. Okay, we will use some complex, so some properties of complex number. So remember this part. So this will be, first one will be x comma x. Second one will be, so, okay, let me write it first, x comma minus lambda y plus minus lambda y comma x plus minus lambda y comma minus lambda y. Okay, by definition, this is norm x square. Second one was minus lambda bar. So, huh?
Minus lambda bar xy.
Minus lambda bar xy
Minus lambda yx.
minus lambda yx means xy bar. Okay. Yx
ये
is
minus
same
minus
as, so
lambda
here,
lambda bar.
so minus minus plus lambda lambda bar. So z bar equal to not z square. If z, so here lambda is an scalar, it may be a complex number or a real number. If real, it is real, then there is nothing. It's only lambda square. If lambda is real, it is lambda square. But if it is complex number, then we use its equality. Z bar is not z square. So we assume this is complex, so it is not lambda square, comma y. But you know y comma y is y square. Okay. Correct?
Yes.
Let me write it lambda bar. Lambda bar. Okay, so now we will get this is norm x square minus lambda bar x comma bar. Take lambda common here. So this is minus lambda xy bar. Oh, this is say y comma x only. Y comma x plus lambda. So it is minus. It will be minus lambda bar norm y square. Correct? Now we choose lambda. Choose lambda so that take norm y square outside, so whatever you will get here, take that lambda, so y by x by norm y square, and it is well defined because y is not zero. Otherwise we cannot define this. We cannot choose lambda equal to this term. Now put this lambda there. So what you get norm x square. And, okay, sorry. You get norm x square minus lambda bar. Okay, but lambda bar is
Value.
this thing. Y comma x bar, x comma y by norm y square minus lambda is y comma x by norm y square, and this is y comma x minus plus. So it would be y comma x by norm y square, y comma x bar by norm y square, and there is one more norm y square. Correct? So see, this part lambda, this part is lambda bar, and this is norm y square. This is norm y square. So norm y square get cancelled. And see this part and this part, they will get cancelled. So you are left with norm x square minus So this is an scalar, this is an scalar. These two are scalars. So it would be by x square. You know, this is same as mod y x square, norm y square. Okay. So this is what we get, but you know this is always greater than equal to 0. So this is always greater than equal to 0. So now bring this part this side. So you will get y by x mod square by norm y square is less than equal to norm x square. And from here to the side y square. So we are done. So we get this inequality. But what happened if this x minus lambda y is, if x equal to lambda y, then it would be 0. So equality hold if and only if x equal to lambda y. Okay. So this is this result. Equality hold if and only if x equal to scalar multiple of y. Okay. Equality hold if x equal to lambda y, and we are done. Okay. Now we define norm like this, but we have not yet proved whether this is actually a norm or not. So let's see that norm x square, when we define this like this, then this is a norm. So means so that this is a norm. So there. What is a norm? Okay, for this you have to prove properties of norms, those conditions. All conditions are easy to see except the
Triangle inequality.
triangle inequality. Okay, but that is also easy to see how using Cauchy-Schwarz inequality that we just proved. So our claim is norm x plus y is less than equal to norm x plus norm y. So let's see this. So consider norm x plus y square. Okay, but by definition this is x plus y from x plus y. Now use those properties of inner product. This will be xx plus xy plus yx plus yy. Correct? So this is norm x square plus xy plus yx. Okay, this is not y, this is x comma y bar plus norm y square. If you remember, z plus z bar by 2 is a real z. You remember this? If z equal to x plus iy, z bar equal to minus iy. When you add these two, z plus z bar, you will get 2 of x. So 2 of x is nothing but 2 real z. So real z is z plus z bar by 2. Okay. So this is a complex number. This is bar of this. So it will be 2 of real of this. Okay. So this is norm x square plus 2 real x comma y plus norm y square. Okay. So but you have this inequality that real z is always less than equal to norm of z. Real z is always less than equal to norm z. Why? Because norm z is root x square plus y square. So x is always less than equal to root x square plus y square. So from here we get this is less than equal to plus 2 mod x comma y plus norm y square. Okay. So now use Cauchy-Schwarz inequality. So this is norm x square plus 2. This part is less than equal to norm x norm y plus norm y square. If you see this, this is a square plus 2ab plus b square. So it's a plus b whole square, like this, x y square. Okay, this is nothing but norm x plus norm y square. So what we have proven is, so x plus y, norm x plus y square. So we have proven is norm y square is less than equal to norm x plus norm y whole square. Take square root both sides to get norm x plus norm y. So this means triangle inequality holds, and we are done. So please make a correction in the notes. I wrote here I wrote 2 real xy less than 2 inner product xy. This is not correct because a real xy is a real number and this inner product is a complex number. So we have to take this modulus. Okay, make that correction in your notes. Okay, I'll stop here. We will see some results on inner product next class. Any
Okay,
doubt?
sir.
Any doubt? Hello? If you have any doubt, please ask. Okay, if there is no doubt, then it's okay. We will meet on Friday. Bye then.